Today's review lecturer is Thomas Mohaupt from the University of Liverpool, and Thomas will be talking about gravity and string theory in general spacetime signatures. So please.
Good morning to everybody, and special thanks to the organizers for bringing us all together here. General spacetime signature, why should we bother at all? Well, I think most of you will be aware of some technical reasons. For example, partial functional integrals are more easily defined in Euclidean signature. And in many situations, they even force us to take complex integration. There are also technical or mathematical uses of multi-time signatures that has appeared in the analytic continuation of scattering amplitudes in attempts towards flat space holography. Some older work I've found here is about metamaterials and exotic matter. Somewhat older is the observation that if you formulate string theory with enhanced worldsheet supersymmetry, you are forced onto a target space of neutral signature with the massless excitations being set to versions of Young-Mills of gravity for open and floating effectively. And lastly, F theory also, which is a way to formulate a non-perturbative approach to type 3 string theory, makes, at least in the original formulation, formally use of two time-like experiments. But here it's more about whether this could play a fundamental role in the context of quantum gravity, because if we get to quantum gravity, I think we still know not very much. And one of the basic questions is what would be prescribed and what is allowed to fluctuate or be dynamic in theory. In general relativity, the metric becomes dynamical. Most people think that in the theory of quantum gravity, topology change is possible. But if we even are allowed to change topology, then why not conformal and hence causal structure, or maybe space-time signature? You can find extreme positions. There are some people who have an approach that you impose causality or the irreversibility of time as the most fundamental principle on which they start. But then again, there are other approaches where people think space and time might be the version of some other structure. Old example for this, but still, I think one of the examples very commercial time is the BLH equation in canonical quantum gravity, which is a Schrödinger equation for quantum gravity, but which happens to turn out to be a stationary quantum gravity. So we are now going to start to desperately look for time. And Page and Wouters have made a proposal that in such a situation where the wave function of the universe is time independent, you recover time by splitting your universe into a clock and everything else, and then relative to the clock, you have holography, a CFT matrix called time also viewed as attempt to, most of the time immersive space, but people would understand space and time should be on the same footing, so the amount of time might also be on the agenda. Do we have a choice in this matter? Well, for my reading, I think there are quite a spectrum of approaches that we have to go about finding theory, in particular quantum gravity. And that is what I would like to call the mode of construction in contrast with the mode of discovery. The mode of construction would be in a sense to start with questions or axioms, right now write down your prejudice of what constitutes into the physics, and then you try to build a theory that satisfies all these criteria. So that's the only way to do science. Sometimes you, in a sense, start not with a question, but with an answer, or at least with a candidate, a structure that you think looks interesting and that you would like to explore. And string theory certainly falls into the category. Historically, nobody even wanted to invent the string theory, but it came to us another way, and then we have explored it by following internal logic of the theory. So I'll try to explain why string theory suggests that we should include exotic theories in Lorentzian signature as well as non-Lorentzian signatures as well, and here consider dynamical change of signature. And roughly one thing that we don't have in product is because I take the attitudes of strings here, whatever it ultimately will turn out to be, should be defined by its symmetry, so an underlying structure. I put both string and theory in quotes because we know it's not exclusively a theory of strings. And it's also not a theory in the narrow of precise sense in which QCD is a theory, because we don't ultimately know what are its fundamental bits of freedom. We are not able to define it by writing down any action or symmetry group which captures it all. And then, following the logic of symmetries, it goes as follows. Generality, when applied to time, implies that at least in type 2 string theory, the theories should exist in any state. And I would use the arguments. And that indicates that these exotic string theories should be part of the full picture, which we can, as far as it comes with the M theory, for lack of better name. And there's also been brought forward argument that the exotic brains in these exotic string theories then facilitate a dynamical change of signature. So they are not only there, but also should be connectable to our world. So the organization of the talk is follows. The first, the view how we come from T-duality to signature change. I will then talk about supersymmetry in general signature, something that I concentrate on some comfortable formal aspects that can be worked out, but which gives us, if you like, the lay of the land, the kind of map of this extended exotic world, which we then move around. And then I'll talk about supergravity and string solutions in general signature, and try to put in a bit of a simple physics motivation of why we should not dismiss these options, but further consider them. And then I'll make an attempt. So I will not be very systematic with references, not comprehensive, but I can refer to the PhD thesis of my former student Martin, who was just traveled to Tokyo to start the postdoc. The thesis is not on the archive, but you can find it on our university repository. And this is the clickable link that uploaded the slides you looked at in the text. So it contains lots of references that Maxime has collected on various thoughts that people had over decades about non-Lorentzian signatures and even complex spacetimes. It also contains quite a lot of good quotations, a few jokes, and at least one hilarious stuff. So I can recommend that. So part one, how do we get from T-duality to signature change? Well, standard way of explaining this is we look at those things on a flat space-time where we include a circle of some radius r. We write down the mass formula. This will have a contribution from vibrations, which are independent of the size of the circle. And then there will be two other kinds of contributions, one from momenta, which we would also have for a particle, but for a string we also have windings. As the formula is written here, you see that has an obvious invariance under simultaneously inverting the radius of the circle in string units and swapping winding for momentum points. That's not only a symmetry of the mass formula, but extends to partition functions of for general and string perturbation theory, and then tells us that the bosonic string of the background coordinate circle is equivalent to the bosonic string on the circle is proportionally all measured in string units. And it has been further extended to tori bundles, and I can derive so-called Buscher rules, which tell you how these equivalent background for the bosonic string look like. What we also note here is that radius to 0 in this game now becomes an alternative decompact. Now, let's move on to type 2 superstrings. And here, this extends with one of the type 2. Here is type 2A on the circle being equivalent to the other one type 2b on the surface of reciprocal radius. Or put another way, the alternative decompactification limit of 2a is to b and vice versa. We should note here that while these theories here are strictly equivalent, once we have a finite size circle, of course, the decompactified theories are not. One is chiral, the other is not. Which illustrates, however, another use that I can give to T-duality, namely as a solution generating technique. Mapping any solution of theory A in theory B. It is often tempting, and I will do the same, to blur this distinction and take situations where, strictly speaking, justify as a solution generating technique to nevertheless speculate what happens in the partner. But we have been warned that there is this line that technically needs to be drawn. So why is type 2a not T? Type 2 has to do with the worldsheet fermions. T-duality can be formulated as a chiral reflection, which say only reflects the right moving excitations on the string, not the left moving. Or the fermions is X therefore by some transformation T, which implements the space reflection on the Clifford algebra. You can work this out, and it has the effect to swap around chiralities, and therefore you get from type 2a to type 2b if you are decompactified in dimension H. Pascal has now investigated an extension. They will allow time-like circles, but found that then you do not get from type 2a, but to a new, to type 2b, but to a new here, which you got to star, and then there's a 2a star partner to type b, which differ from the unstarred version by certain signs and phase factors in the partition. This has strange effects, for example, in the effective field theory, corresponding to supergravities, have sign flips for all kinetic terms in the Ramond sector and phases in front of the kinetic lines. It also has effects on the brains in the theory. So let's recollect in type 2a and type 2b, we have DP brains, which we can view as solitonic open string sectors, which we add to a theory which otherwise only contains closed brains. We allow directly boundary conditions in some spatial directions with Neumann boundary conditions in the other space directions in time. Now, T-duality exchanges Neumann with Dirichlet boundary conditions. So if you do a T-duality from type 2 to a type 2 star theory, you now get what are called T-brains, which have an event-like localization in real time. So like instantons, but real time rather than imaginary time. And this has further effects. Because let us look at S-duality. S-duality in the type 2b theory is the self-duality under inversion of the coupling. That strong coupling type 2b string looks the same as a B coupling, but this is facilitated by swapping fundamental strings against D strings. Now, if I go to the type 3 star theory, the B1 brane of the string has been replaced by 2 brane, which now has a Euclidean world volume. So the theory is not really self-double, but it's mapped to a real theory, mapped to type 2b prime, where suddenly fundamental strings have a Euclidean worldsheet theory. And this in turn affects T-duality in the following way. If you have fundamental strings with Lorentz signature and apply T-duality, then the signature of the target space the string propagates in remains unchanged. But if you have fundamental strings which are Euclidean and you apply a T-duality, then this flips the sign of, then it flips around the signature of spacetime either in, it now depends on which direction you. I think I have a super tool plus minus sign here. So it's just one entry which gets flipped. So the signature really changes, say, from Lorentz to Euclidean or to 2 times. I think given in terms of Buscher rules, the Buscher rule, usual Buscher rule is a symmetric coefficient gets inverted, but it has a phase factor which counts the number of time-like dimensions. And while for Lorentz signature, you don't have a sign, you have one if you do it in the signature. By the way, it's the same type of sign flip that you get when you do Hodge duality in any theory with any p-form field. But T-duality is not quite Hodge duality because we are not swapping out the gauge potential for dual gauge potential, what we are doing is we gauge a rigid symmetry of the target space and then integrate out the original coordinate and makes the Lagrange multiplier, which we need to import flatness of the gauge connection to make it the new coordinates. So it's technically simple and has the same effect on this type of term as regards to sine. So suddenly we get an extended map of dualities. Originally we have a space-like type duality between 2A and 2B. Now time-like T duality brings in B star and A star theory, which in turn are related by space-like T duality. And once we do S duality to time to 2B prime, there's an extra chain of what my student I call mixed T dualities, which change signature. You will have a 2A theory Euclidean and 2A signatures and goes on to a type 2B theory in signatures 3,7 and so on. Moreover, then later the case was made that this kind of signature change could be a dynamical effect. Along the 490s, gentlemen were interested in gauge theories built, or not on the group, but on the supergroup, and they found they can realize this with open string sectors if they do certain sign flips on the ends of open strings, which turn out to give some of the B planes a negative tension, so called negative branes. And here I also n plus number of normal positive tension planes, but n minus the number of negative tension planes. These are there. You can see these supergroup gauge theories. Now let's look at corresponding supergravity solutions, the typical form of stable B-brane solution. The deviation from flat space is described by a harmonic function with respect to all transverse directions. And we have a factor here which depends to which the normal planes contribute positively and the negative planes contribute negative. Now, if you have more negative than positive planes, then this function will have a zero and a sign change before you reach R equals to zero, which is the location of the horizon. So these are spacetimes where you move in from asymptotic flat, and then before reaching the plane, it hits a naked singularity, and the place-based vector negative tension brane is hidden in a bubble which lies behind this naked singularity. Now they made a couple of observations, namely, well, now you can lift, say, let's be concrete, let's look at a negative D0 brane. D0 branes can be lifted, it can be lifted in 11 dimensions. 11 dimension supergravity, or that's called M0, and then we have a PP wave. But then if you look at the PP wave line element, so that H has a zero, the metric is perfectly fine. However, it has a sign change, and if I then make my dimensional reduction once I've crossed inside the bubble from one dimension above, I end up in a space-time which is Euclidean in signature. And that's then what they say. What is inside the bubble behind the naked singularity is space-time which belongs to the exotic Euclidean type 2A theory, and relative to this theory, the D0 brane is positive. So negative branes are normal branes, but with respect to an exotic type 2 brane theory, the naked singularities are somehow interfaces between these theories of different signature. Few more observations that I want to quote from this paper, so that then I do a kind of brane scan and also match it with holographic dualities. So once you buy into this, you also get then exotic holographic dualities, which apply to this supergroup of gauge theories. Then the supergroup gauge theories have also been explored a bit. They are strange in the sense that they're necessarily non-unitary. They have negative energy states, but roughly speaking, everything else works like in supergroups. You have consistent Feynman rules and perturbations here. You find it with the arguments for the beta function is n equals to supersymmetry. You have 1 over n expansions. In n equals 2, you have Liebert curves. You have vectors of instant calculus, which tells us that it is formally the path integral for such a theory localizes. And there's some matrix models that might provide an honest non-perturbative definition, pending, of course, the question of how we interpret such a theory physically. They also found some things which are not so nice. One typical feature of theories all the time, like complexification, is that the use of effective field theories is more questionable than usual, because the Kaluza-Klein towers do not necessarily decouple. I have nothing to add to this argument, but there is more at work naively with effective field theories. I would also mention perspectives for model building, which have been explored a bit already, because Hull made the observation that in these exotic supergravities you can have de Sitter solutions, so naturally interested, and then Lobenhagen and collaborators looked at the option to build de Sitter cosmology in exotic frameworks. The idea was along the lines, okay, the closed string sector theory is very bizarre, but let's be agnostic about it and just look at frameworks embedded into this, and let's see whether we can have reasonable physics through an open string vector on these frames. And my rough understanding of that work is that it's almost not quite work, so there are quite a few of these potential issues can be resolved by tweaking your frameworks accordingly, but ultimately they were still unhappy about some features, and that I suppose I don't read more about this. So, as Roman said, be aware what you are buying into. If we enter this exotic world, we have to worry about stability, causality, unitarity, and the effect field theory. Also, they always ask myself, yeah, but what would it be like to live in such a state space-time? And you might want to add some down here. Of course, I could now end the talk, but I have some reasons to continue. So let me give you some reasons why we should still study this exotic world. One is the point that Casal already made in the book before, where developed time like 2 duality defined type 2 and type star. As long as you have a final circle, this is just a funny rewriting of the original type 2 theory. So the type 2 star theory looks bizarre, but ultimately it is, if you like, a field definition of type 2. It's just a conventional physics in an unconventional way. If I go to the other extreme, they are lived just with effective field theories and forget about everything which is not massive, then time-like dimensional reduction is a valid time or not solution generating technique. If I'm interested in time-independent solutions in some theory, I can reduce over time, solve in a Euclidean theory that way. Moreover, sometimes I have more than one way to live back to 4 dimensions, and this is kind of the field theory or supergravity version of T-duality, namely alternative lists of a single reduced or lower dimensional solution in different ways to 1 dimension height. More generally, when we reduce by dimensions, we uncover hidden symmetries, or if you like, U-dualities. Was stressed by David and Nicolai in their seminal work on 11-dimensional supergravity already, that these, whatever you call them, are not just symmetries of the reduced theory, they are hidden symmetries of the full theory that become visible if you restrict the manifest spacetime. So there are some hidden symmetries competing in a sense with the spacetime symmetries. So in a sense, we are asking here for the specific Gerov group, and I will say a bit more about the Gerov group. And the first time where I kind of also touched with something that Gabi will talk about on Friday, because gravity also, the hidden symmetries are not restricted to supergravity. Gravity has them, and they lead to integrability in certain sectors of gravity. And that's what gravity, among other things, we'll be talking about. Also, I think just abandoning what we ad hoc, I would like to have a clear criterion which cuts out what we should discard as unphysical and what we should keep. But finding such a precise demarcation criterion is quite subtle. Time permitting, I will say a few more words later. And I will make an independent physics case while studying time-like T-duality and signature change. That is interesting, even from a humble 4-dimensional perspective. You can phrase this question without talking about string theory at all. So part 2, which I said is now a bit about formal aspects, about having an overview and a clear systematics of all these topic theories. And I will just also need as a tool to build up what I will form. For supersymmetry algebra is typically write and down as supersymmetry. We have some supercharges, which have a spinor index, and then we have extended supersymmetry of some additional multiplicity index, and is anti-commutative translation into the momentum operations. To write down such a bracket, I need to use charge conjugation matrix because I need to make the right-hand side symmetric in all its indices. If it's extended supersymmetry, then I have also a matrix which acts on the internal indices, and then the right-hand side must be symmetric in the multi-indices which pair internal. You can always view this as not only as a real, but as a complex bracket. And that's in a way that, in fact, the way that you encounter when you write supersymmetry algebras in terms of symplectic Majorana spinors. And for my purpose, I would like to adopt this way of writing supersymmetry algebras wholesale for all possible situations. So I have a complex super bracket, which is defined by my charge conjugation matrix and choice of a matrix on internal indices. And then I obtain a real supersymmetry algebra by imposing the reality condition. To apply a reality condition in spinor space, I need a B matrix, so it's some matrix that is related to the C matrix, which allows to impose a reality condition on spinor representation. And for the internal matrices, for the internal indices, I would also need a second matrix pair. So I have two pairs. The first pair defines the complex super bracket, and the second pair that takes a reality condition, and this is also spacetime. Now, I work with mathematicians, and they talk differently from us, so it makes sense to also formulate this in a way that the mathematicians can understand what you're talking about, so that they can help you. So for a mathematician, a super bracket is a bilinear form, which is real, symmetric, vector valued, non-degenerate, and spin equivariant, which means our language. Luckily, Alexei Portes has classified all those super brackets on their language bilinear forms for any number of dimensions, any signature. There's also an extension to this, including BPS charges. The work is Van Foren and I think different, but I won't use this here. Yeah, for physics.
So in standard n equals 1 supersymmetry in okay, good. In standard n equals 1 supersymmetry, like when we have standard signature, we have a kind of uniqueness for the algebra. Yeah. Does this is this statement still valid when you go to more general?
No, uniqueness, but because it's of the test, the similar of this has already been out in 2 dimensions.
Okay.
But a bit of the generalization. I will give some more.
Okay, cool. And will you also talk about the representation story of things?
We haven't worked out. Well, in a sense, what we have done is representation comes of the because I will talk on this from start. More on the representation of the algebra field. I'll say it one thing. Right. So that's very nice. The specification. So in a sense, these are all supersymmetry algebras, but not quite in the form that we want to use them, because the super brackets form vector spaces. So they kind of continuous family. The form, to be precise, the form vector spaces if I also include degenerate super brackets. In particular, every vector space has the element 0, which corresponds to a bracket where I send everything 0. That's not a super bracket at all, but it might also contain, if I look at super brackets for an n equals to 2 supersymmetry algebra, and the degenerate brackets might also include n equals to 1 algebra. But here, for my purposes, the classification problem, first the super brackets come in continuous families, and then we need to sort out which of them are equivalent, which are non-equivalent supersymmetry algebra. Concept which helps the Schur group, these are just the linear self-mappings of the underlying spinor space, which conjugate with the action of the spin group. And this Schur group always relates equivalent brackets to one another. Interesting question is it already all? So are the inequivalent super brackets just the orbits of the Schur group? Because then you have a well-defined mathematical problem. You have group actions on vector space and classify orbits. Also, some of these elements of the Schur groups leave a particular bracket invariant. This is what physicists call the R-symmetry group. And as an isotropy group of some group action, it is the same for all orbits. Another question. Orbits normally will have different R-symmetries. Are then the inequivalent super brackets just classified by a list of R-symmetry? That would be very nice. Partial answers to this. Up to fine print, inequivalent super brackets indeed correspond to Schur orbits. There's some fine print to this which has to do with action of some elements of the pin group which are not in the spin group. The theorem that we derived is that long. It's complete but not usable, so we then have a collection of lemmata which reformulate in a way that you can use it back. Experimentally, and we looked at this in completeness for n equals 2 superalgorithms, mean algorithms 8 real supercharts 5D and 4D, we found that in this case the find that it's not relevant. Inequivalent super brackets correspond to orbits of the respective Schur groups, and as long as it's extended supersymmetry, where the R-symmetry group is continuous, the inequivalent super brackets are in one-to-one correspondence with R-symmetry groups. So in these cases, classifying R-symmetry group is all you need to do. And then what my student Louis did in part of his PhD thesis is they provided this classification, or at least of possible R-symmetry groups, again for all dimensions of all signatures. We wanted to have a construction which works uniformly across all signatures, and then to take into account, of course, that spinor change by dimension signature between Dirac, Weil, Majorana, Weil, etc. So we wanted something formalist, which is uniform. And the useful thing to do is to do some generalization of symplectic Majorana. The philosophy is we first construct complex super brackets in a given dimension, or super brackets, complex super brackets in a given dimension, this part, and then we impose all possible consistent reality conditions to get the real algebra in any signature. Also, a principle is, and for which the multiplicity spaces are useful, and therefore we sometimes introduce them even if they're not strictly needed, is that we want to isolate the action of the R-symmetry, so that essentially by looking at the algebra, you immediately know what the R-symmetry are. So you can look then at the supersymmetry algebra and you know what it's are. It's similar but not quite identical to what Hall did when he introduced the supersymmetry algebra for type 2 star, and I believe he had also had earlier work we observed similar phenomena in n equals to 2. But I think at our formalism, M and L can be chosen independently, and we first fix the complex super bracket to a standardized form, and then scan all the forms. Now, the master tables are quite complicated, but let me walk you through a few cases which relate to what we see in string and M theory. Simplest case, D equals to 11. This you can do without much formalism. Smallest algebra 32 real supercharges, one single Majorana spinor. This exists obviously in those signatures where I can have Majorana spinor, which is Lorentz, but also 2,9 and 5,6, which matches the exotic M series that this Hall found by lifting up this exotic pattern. So that's nothing too demanding. Let's look at D equals to 10. The story becomes more interesting. We take the smallest algebra, 16 real supercharges. This algebra is now chiral. And we all know that we can have Majorana Weil spinor whenever the signature, meaning the difference between these entries is 0 modulo 8. So we probably have already from this figured out that apart from Lorentz signature, also in signature type 5, you can have such a supersymmetry algebra, and this corresponds to type 1 heterotic, and the exotic partners also found by us. Now, it's actually a bit more complicated than just showing that Majorana is this. Of course, what you also need to know that the super bracket has a right-handed supercharge, the right-handed supercharge. The super bracket itself must be chiral, or as we call it, of orthogonal type. This depends on the dimension. It's not true in 4 dimensions. In signature 2,2, we have Majorana-Weil spinors, but the super bracket will always pair right with left. So the smallest algebra that you can have in signature 2,2 is not one Majorana-Weil, but one Majorana. Yes. Sorry, what?
So why do you, is there some intuition why they're like, why in 4,6 you see this structure that you quote there, or no structure effectively? Or
yeah, there's no supercharge for the smallest thing. Just in this case, you can just say there's no reality condition which is compatible with the super bracket. Yeah, the super bracket exists as a complex bracket, but if you call it the reality condition, it becomes the enigmatic element. And yeah, and principally it can survive with module H, but for us the complete logic is the complex super bracket is orthogonal type, meaning it has right-handed spinors. In our table, then for such types, the R-symmetry group is the orthogonal complex group, but it's discrete. And it doesn't change if you impose the reality condition, because in these signatures, we have the reality condition while compatible that you can apply, and then the dimension that flow, and in these other signatures, the reality condition just gives back not compatible with. So the reality condition would pair right with left. But other super bracket is sensitive. Okay. Now the fun starts with understanding d equals to n equals 2. So I guess if the answer first, okay, so if we collect the chiral and non-chiral algebra, the 32 field supercharges, which you can package as Majorana-Weil spinors. You see that there is a lot of different choices in signatures 1, 9, and 5, 5. But the generic pattern across signatures is always an alternation between a single chiral and a single non-chiral. So it always goes, if we start with Euclidean signature, to A to B to A to B, non-chiral, chiral, non-chiral, chiral. Here it becomes more complicated. How does this structure arise? Let me guide you through this. So the first step is the complex super bracket is orthogonal, or in a sense chiral. This all depends on the dimension. According to our list in even dimension, this is the product of two complex orthogonal groups. With these entries adding up to 2. 2 ways to split. Either I put n equals to 2, n equals to 0, or I split it democratically. And these are the two complex super brackets which I can now scan against all the available realities. There's the signature that the number of time-like directions is even. In this case, the reality condition is while incompatible, or if you like, all reality conditions are non-chiral. And then the supercharge is the Majorana spinor, the algebra is non-chiral, and in this case, the R-symmetry gets reduced because the reality condition mixes up left with right. So it goes down from a product Z2 times Z2 to Z2. Next are the signatures with an odd number of time directions. Here the reality condition is chiral, but we still have a subdivision. Why is that? Well, we impose a reality condition, but the reality condition not on spinor space, but on spinor space multiplied with the internal multiplicity space. We have now 2 supercharges, so we have an internal multiplicity space. A real structure on a product space can be a product of the real structure, but can also be a product of Witten structure. This makes the difference. In signature 3,7, we have a reality condition, but the spinor representation itself only carries a quaternionic structure, not a real structure, so I don't have Majorana-Weill spinors. In this signature, I can only have chiral algebras, and the R-symmetry group is, well, a real subgroup. Now we go to these signatures, where we have a product of two real structures, so the spinor representation carries the real structure itself. We have two Majorana-Weill supercharts that we can arrange chirally or non-chirally. But we don't get two, we get four different algebras twice that. And now we have to look explicitly at the consistent reality condition. And there are still, in both cases, certain plus-minus assumptions are fixed, and whose choice is the inequivalent algebras. For the chiral algebras, it is easy to see in terms of the R-symmetry group, because the complex R-symmetry group, the complex R-symmetry group can be two different forms, I think. The standard one or two with 2B, but there's also the consistent algebra with O11, the twisted version, which is then type to be started. For the non-chiral algebra, the R-symmetry group is Z2 times Z2 in both cases. So the R-symmetry group doesn't capture the difference between the two algebras, and that's always the case if the R-symmetry group is discrete rather than continuous. But still, if you look at the reality conditions and classify them, we see that there's a sign which we can pick as a plus or minus given a standard and a non-standard algebra. Okay, this was very detailed. Now let's try to do some T-duality with this, or now play the game. Let's predict the T-dualities. How much can we already say about the network of T-dualities from this algebra? So I need now to look at all the dimensional reductions or mathematical contractions of all my 10D algebras to 9D. This is listed here. The 10-dimensional theories are symbolized by the corresponding label for the strings theory. That in 9 dimensions, the algebras are represented by the R-symmetry group. Blue arrows are space-like reductions, red ones are time-like reductions, and then above here we indicate then where such arrows can be combined in a reduction lifting procedure with this relative. For example, here we have space-like T-duality from A to B. And here we have the time-like T-duality to A to type star. And in some cases, we get mixed T-dualities, say from type to B star, type to A, which change chicken. I should, however, mention stress that this does not give you the full information. For example, I'm blind against the distinction between 2B star and 2B prime. It's the same supersymmetry algebra. They couldn't have predicted that it must, if I really look at the physical theory with this partition function in full glory, it must be 2B prime, which I T-dualize into a non-Lorentz signature. But at least you can get a roadmap of all the possible options. And you also see that this exotic string series fill out all the possible algebras across all signatures. So all possible algebras are realized. Now, the last part of the talk, I want to push the discussion down to 4 dimensions. So let me use my tables to tell you a bit, just based on algebra, what I should see in 4 dimensions concerning a network of T-duality. And I will do a reduction of type 2 on the Calabi-Yau threefold. So I go to n equals to 2 series with 8 real supercharts. I've listed the signature. I've listed the R-symmetry. The Lorentz signature, that's the standard one. This is compact R-symmetry group, but there's also twisted version. There's a neutral in the Euclidean signature. There's a single R-symmetry. Now, what can I learn from this? Well, I have 2 kinds of meta-multiplets, vectors and hyper. The vector multiplication field and a complex scalar. Hypermultiple is 4 real scalars, stuff you can think of as quaternion. Now, so that in the R-symmetry group, always it is locally factored into the abelian to non-abelian part. In the abelian part acts non-trivially on the scalars and the vectors, and the non-abelian part acts non-trivially on the scalars and the hypers. For example, in the standard case, this U1 here acts as multiplication with a complex unit I, or more geometrically as multiplication by an integral complex structure on the scalar manifold, which tells me the scalar manifold better be a complex manifold. Well, it's in fact a scalar manifold, of a special type called special scalar, because a special type of scalar manifold where all the information is ultimately encoded in a single holomorphic function. SQ2 acts non-trivially on the hypermultiplet scalars, and there it acts as multiplication with the unit imaginary quaternion, which tells me that this manifold better carries the quaternionic structures. And indeed, hypermultiplet geometry is famously quaternionic scalar. I can then go through this list, see how this factors change, and predict how the couplings of my matter field should change. For example, if this U1 is replaced by a non-complex version, then instead of a complex geometry, I get what we call paracomplex geometry. So the complex structure, which squares to -1, is replaced by a so-called product structure or paracomplex structure, which squares to +1. And so there's a whole bunch of families called paracomplex geometries, which are modeled on the ring of paracomplex numbers. So I get from special scalar to special parascalar. And similarly, for hypermultiplet geometries, I get from quaternionic scalar to parascalar. So that's what I can immediately tell by just looking from a table, what should happen in the Lagrangians with a scalar field. There are some things that I can't tell from the table, which is annotated here by the ±. What also happens to Lorentz signature theories is that the Maxwell terms differ by sign. This is not encoded in the algebra, this is just a matter of the particular representation of the algebra that we have to work out separately, but which is fixed by the supersymmetry algebra that we have. Now, if I want to do T-duality before series, I compare this now with what I can predict in 3 dimensions. So again, I make my list. This time I have 3 algebra in Lorentz signature, but one of them is orphan. It's not reachable by dimensional reduction. I'll ignore it. But otherwise, you have the standard algebra. Factorizes as a product of these 2 complex groups. And this also is consistent with the fact that in 3-dimensional supergravity, the hypermultiplets form a general product. It's product of 2 quaternionic scalar spaces, which, by the way, is not product of quaternionic scalar spaces, it's not quaternionic scalar. What's important is the product is 2 decoupled quaternionic scalar spaces which form talk to each other by gravity. So that's the standard case, and then I see the worldsheet here if I go to either the twisted version of the algebra or to the Euclidean signature, and namely in one case, one of them becomes para and the other. So, what is now what we would expect if we just push down our network of T-dualities from 10 to 4 dimensions? You would expect to see type 2a, b, related by space-like duality, related by time-like T-duality to type star, which also expected for type 2 prime, we can find mixed T-dualities, which bring us to the Calabi-Yau complexifications of the Euclidean and the neutral signature to X theory. But what is not clear from the 4-dimension perspective is whether we still have an S-duality to go from B star to B prime, because in 4 dimensions, for n equals to 2, the S-duality only exists exceptionally. It's not a generic. And you might also wonder how are we able, because it's the same supersymmetry algebra, to distinguish type 2 B star from type 2 prime from the 4D perspective. Now for this, you now need to go to the next step, namely construct Lagrangians, look at the coupling more explicitly. The samples here a bit of literature, 2 methods mostly. If you can reach your theory by dimensional reduction, that's the quickest way. Some people, in particular Wafik Sabra, have also used Helix spinor equations, which you can continue to other signatures and then read off bosonic field equations to reconstruct one. What you can also do, your question is, you can take the theory and Lorentz signature, complexify, and then apply all the other possible reality conditions. That's for which this formalism that we have is made of, and we have applied it in full generality to 5D offshore vector mode with all fermions, auxiliary fields, everything. And we took the Lorentz theory, complexified it, then imposed in this formalism the other reality condition, we get the complete picture. We have applied it since that because all the other results that we're interested in had already been previously been obtained by other means. And so the method, I find the method quite economical, but you don't necessarily need to duplicate known results. I should also mention that a similar philosophy has been applied previously to maximal 10D and 11D supergravity by Blackshaw and a few other people who found that there are 3 complex master series which give you all the maximum supergravities in 10D and 11D for all size. Okay. Now, let me show some of the more gruesome details. So what I've written down here is how vector multiplet, bosonic part of the vector multiplet Lagrangian looks like if you do type 2 on a Calabi-Yau threefold. Let's first go over the structure that these Lagrangians have. So you may think we take the standard Lorentzian type 2 theory. So you have an Einstein-Hilbert term. So gravity combined with vector multiplets. That's bosonic part. So you have Einstein-Hilbert. You have a nonlinear sigma model with some scalar ZA. You have a Maxwell term, and you have an FHF term, and the red guys are coupling functions which depend on the scalar set. And this can in general be very complicated, but by this underlying so-called special geometry, ultimately you can compute all these red coupling functions by knowing a single polynomial.
Yeah. Microphones in here. So can you say a bit more on like what would be, say, the general ansatz or the general structure of these functions? And now when you impose the additional structure, how they are constrained? Like,
so for supergravity, you can write out every holomorphic function that you like, but this will give you a domain in which your couplings will have, if you understand that case, the required positivity property for the again. But you can, from a supergravity point of view, that's all that you can do. Those coming from Calabi-Yaus have a special form, of course, because they are free potentials for scalar or complexified scalar or for complexified geometry. But from a supergravity point of view, can't say more that locally the complex function, if you impose positivity, that you can follow your couplings, that you can find the maximal domain that these conditions are met.
Yes, and so how are they more constrained now? I mean, I guess that would be a general answer which you would write down. Can you say explicitly how the duality?
We have caveat of that, of course, done explicitly is the complexification of the Calabi-Yau manifold, and then I know all F is related to your Calabi-Yau.
But the duality does not give us anything else.
Which duality? No, I'm not getting the duality. I'm just taking stock.
So this is just the general answer.
It's not an answer, but for any particular Calabi-Yau or what that fits. And supergravity does relative function. Duality will come next step. I'm just what I'm just discussing is how do these couplings modulate if I go over my duality. Yeah. And for this, I have 2 kinds of switches. One type of switch is where I'm going to have to start or signatures. A certain sign flip, which I can parameterize, and which for each of these theories I know. And the other change is whether the fields that are really honest complex fields, so that are scalar geometry, or whether they are para-complex fields that are para-scalar. And this is both in the non-logarithmic technique I have the para-complex geometry. But we have concept of para-holomorphic function, and it's consistent with what happens in Calabi-Yau complexifications because to just pair the moduli from the scalar moduli, just pair the scalar moduli the different ways with all the different models. So this gives you the general scheme how vector multiplets look like. That's a hypermultiplet. So if you obtain the hypermultiplets, then the scalar manifold in general is a standard case, the quadratic scalar manifold. And if it comes out of the Calabi-Yau manifold, it's a twisted product between special scalar manifold, this part, and the group manifold, which is related to all other fields. Now this product is visible in the sense that what I have here for the fields is secretly a left invariant metric and some group manifold, but changes if I change that, because these matrices here are functions of that. So this sense is private. But this is the type of quadratic scalar manifold which you get out of the Calabi-Yau complexification. Of course, everything to lowest order and alpha prime. What are the switches? Again, explicit sign changes because of epsilon. And sometimes you have complex fields sitting in here. Sometimes you have paracomplex. And that's where type 2b star sticks out. It's a para-quaternionic scalar manifold. A distinguished submanifold, which we call the base, is in this case not scalar, but parascalar. Now, if there was an S duality, which somehow could turn in 4 dimensions, which somehow could turn the B star into the B prime, it would have to mix up these fields such that instead of a scalar manifold here, I get a parascalar manifold. But this thing here can be arbitrarily complicated. It depends on a principal arbitrary complex function or a complex function that is dictated by my Calabi-Yau. So I can't really see how an S duality in this setting could work, except for fine-tailed or very fine-tuned version form. Now, Dr. Casali always said, yes, but in 10 dimensions, ultimately, you still have an S duality, which you don't lose. That may be, but from a 4-dimensional point of view, I can't see how this S duality would work in general. And therefore, the resulting picture of T duality is followed. Here I write again down time-like and space-like reductions from 4D to 3D. But only those arrows which are of the same type can be composed to give you a T duality. We have a T duality from 2A to type 2B, which is space-like, and another from 2A to type B star, which is time-like. But due to the fine point that this here is the same supersymmetry algebra, but the representation of fields is different because the scalar manifold has a different structure. I have 2 separated T duality orbits, where here I have another orbit of signature changing T dualities where I go Euclidean 2A, type 2B prime, neutral signature type 2A. And without S duality, I can't connect these 2 orbits together. That's all I can say. Good. Now I wanted to come part 3. Of course.
So this is about this tension that you mentioned about S duality in 10 dimensions that's not visible in 4D. If you were to add perturbatively higher derivative corrections, say alpha prime corrections, will that help the situation?
Well, I don't know, but as far as I know, taking into account all possible corrections, it is feasible that you have S duality realized on these quaternionic scalar spaces. So my mathematics co-worker, Vicente Cortez, had relatively recently a paper where they identified some cases where indeed you could have S duality for hypermultiplets where you include almost all non-perturbative corrections.
And these are non-perturbative in what?
Yeah, it's all these brane instanton corrections that you can have. Yeah, so the hypermultiplets get various types of corrections. I think there's one type of correction, but which one still does not know how to incorporate. But in principle, by chance of dualities, one thinks that one could get these hypermultiplet metrics in principle exactly with all non-perturbative corrections.
Thanks.
If I were to look at the two theory, gravity coupled to vector multiplets whose part of the space is not parascalar, would is there something like an attractor mechanism there in place as well? If I were to look at,
yeah, let's say I don't see why not, but I haven't looked at solutions of these theories. So I haven't looked, but I've collected a few references, but I'm still to read them myself. But some people have worked on solutions in this series, so one should be able to look it up. I don't see any obstruction, let's say. These neutral signatures seem to be giving you even more solutions than you have in Lorentzian. That's my impression from glancing over the references. Any other questions before I proceed?
Solutions. The solutions are yeah, but if they exist on one branch, I mean, they exist on one of those nodes, then they exist in other nodes that are connected to it, right? I mean,
yeah. So you can ask. You should be able to T-dualize your solutions around, and that should be safe behavior. That's a good point. Yeah, that's your point.
Yeah.
I think that makes sense.
And this is also goes through in the mixed T.
I don't see that mixed T is in this respect as a solution generating technique.
Yeah,
I mean the theory you might throw out the theory altogether because you say I don't like negative flip signs of the kinetic energy.
You can just go to the other representation.
Yeah. Then everything goes.
Yeah. Right.
Okay, so then about solutions, to consider the following, I consider a space-time which contains a non-extremal horizon, non-rotating. Yeah, but this is a generic form for a non-extremal horizon. I assume that the solid is a Killing field, which is shifted in the coordinate T, parameterized by one function f of r, which I assume has a simple zero, in other words, a sign change. And this is local description for non-extremal Killing horizon. Already in early days of T-duality, people have looked at T-duality of T-duals of Killing horizons, and they found it's a singularity. And I haven't read much in the literature since then, but I'm still a bit confused and interested in finding out what's going on here when we T-dualize a space-time containing horizon, and specifically a non-extremal. So if we perform a dimensional reduction of this from 4 to 3D, which we can do because we have a Killing vector, then we get a three-dimensional metric and we call it a Klein scalar, and we see that the function f is positive, this is Euclidean signature, where it's negative, it has Lorentz signature. So in this reduced theory, we have a signature change at r equals r star. And of course, at this point, not only the solution, but the underlying theories are singular. But it leads to an honest-to-God event horizon. In this sense, we know quite a few examples of, in a sense, physically acceptable signature change, if you just take the perspective. The example that I gave you before from the Dykra-Buffett paper was doing the same, something similar with the PP wave, but I find this even more central, and therefore it's a class of examples that I can't explain. If we add a little bit of string trimmings, then you might already see here that the way I've done the reduction here is the one that we would do if you relate two particular conformal frames, namely string frame to string frame from 4 to 3D. So what I'm tacitly assuming that I have an embedding in the string theory, that I start with this line element, but dilaton and B fields are zero in that 4 dimension. Extra information that I then get is the relation between the 4-dimensional and the 3-dimensional dilaton, which goes to the Klein scalar, and you see immediately, if I now would be to T-dualize it, what will happen in any case is the following. If I start with the trivial 4D dilaton where this is 0, and I make a T-duality, then the T-duality should flip the sign of sigma, so I will generate a three-dimensional dilaton is T-duality invariant. So by lifting back to 4D, I will dualize such a solution, this trivial dilaton, always into a solution with a non-trivial dilaton. We also say that, of course, for this type of solution, the T-duality that I apply is like on one side of the horizon space. Thus, the following questions are closely related. What's the T-dual of a non-extremal Killing horizon? And when can signature change in D dimensions be lifted to a smooth geometry in D+1? And I think that's a good motivation to look at this, even irrespective of things. As a concrete example, currently we are trying to both attack this as just a generic thing where we don't assume anything about the function f, except that it has a simple zero, and you can say a lot about this based on this. But also a favorite example for somewhat idiosyncratic reason, because at some point, well, different colleagues stumbled into this, and this has also been discussed before in the context of cosmological solutions. I remember some illuminating discussions that we had in Liverpool when we had found these solutions, were not quite sure what they meant. So this is technically one extreme derived from Nordström, but with spherical symmetry replaced by planar. Okay? But it's properly interpreted as a cosmological solution because it has the following structure. If you follow the coordinate R from the inside out, then R equals 0, so the singularity, up to R star, which is the 0 of the function f, static, horizon, outside, R becomes time-like, and depending how you continue, it's an expanding or contracting cosmology, and the maximal extension is a cosmological bounds which interpolates between a contracting and expanding cluster cosmology, asymptotically, with the bounds created by having these time-like singularities, which, as I will show in a later transparently, you can lift to some well-known brain configuration in 10
So in the previous slide, the R equal to R star, when it was the previous, or maybe that I was talking about the dilettante. Yeah. So at R equal to R star, where f is 0 in the
star between 0 and infinity.
Right.
And that's where I have the 0 of the function f. So I say,
okay.
So local description is just a function f, which has a simple 0 at some point R star, and I consider an open interval around this 0. That's what we're studying in horizon in generality. In my specific model, I have a singularity at 0, a horizon at R star, and an asymptotic, which happens to be a Casimir.
So do you get in 3 dimensions, do you get a curvature singularity in the string frame? Because that's with respect to
I will give you the singularities in 4D.
Okay, but you don't make like a.
I've not looked at 3D. Okay, so don't let me look at, but proceed. So yeah, again, philosophically, in principle, lots of this discussion you can do with a gravity person by saying I reduce and lift, but to get this extra interpretation and feel for the situation, you better pick a string embedding, because only if I've embedded the string theory, I can, for example, talk about a string conformal frame. Because for this, I need to know where's this dilaton in my theory, and maybe my B field, and maybe which fields come from, say, Lewis-Schwarz, or Ramond, if I embed into type 2. Therefore, I'm interested in this, and for space-like T-duality, it looks like this. If you take Einstein-Maxwell, and just T-dualize it on the node, it gives you an Einstein-Dilaton axiom system. The dilaton is a dilaton, but not necessarily a string dilaton. But I can embed it into an n equals to 2 theory, which is n equals to 2 supergravity multiplet plus 1 hypermultiplet, which I take to be what is usually called the universal hypermultiplet, both concerning its choice of the target space, but I can then obtain it from any Calabi-Yau compactification of type 2 as the universal hypermultiplet containing the dilaton, because any Calabi-Yau reduction of type 2A type 2B admits a truncation where I freeze all the scalar and complex structure moduli and any Ramond moduli sitting in the same supermultiplets, which truncates out all meta-multiplets except one, and that's the famous universal. At least analytic order alpha prime in these strings, which is unambiguous. So I have a nice Calabi-Yau embedding. I can also lift it over torus, which is very nice if you want to lift your 4-dimensional solution to brane configuration in 10D. Then I better go over a torus and not around the Calabi-Yau 3-fold compactification. And I think I put in some honesty questions here, because there's some things that I'm convinced are obviously true, but which I still need to check fully. The solution that the way we got to our planar Nordström solution was as a special case of a larger class of solutions to the so-called STO model. And if you take the STO model, which is normally understood as a model with 3 vector multiplets, and complete it into a T-duality self-invariant model, then it's a model with 3 vectors and 4 hypers, which I think the Sen-Wacher STO models that Gabriel once pointed out. And I believe this is another way of embedding it through an orbital. Anyway, there are these three ways of embedding what I'm doing into type 2 string theory in 10 dimensions. Well, if I go into time-like T-duality, then this diagram gets a bit more complicated because now every of the points that I have before splits up into a standard version and a flipped version, and time-like T-duality always sends the standard to the flipped version. Therefore, this diagram I've mentioned it here for completeness, but of course it looks at first glance probably a bit confusing. But this is kind of the full story. If you want to include time-like T-duality, then every model comes in a plus and in the minus version with some sign flips that we have full control over. Anyway, what we then have shown in the papers soon to appear is that, yeah, so what have we done? We have taken this model n equals to supergravity plus universal hypermultiplet and done the reduction lifting procedure, both over space and time, but in the string frame, proper identification of four-dimensional dilaton and so like, and we have Buscher holes derived for this system of gravity one vector and four scalar fields. They take, for those fields which descend from an S sector, exactly the same form as the Buscher holes in 10 dimensions. We also have some fields like the Maxwell field, which come from Ramond-Ramond fields. For these fields, then we get Ramond-Ramond sector T-duality rules, but of course these are non-universal because the content of the sector is non-universal. But as far as the metric and the dilaton that we generate, it looks despite the Buscher holes. And then we can look, coming back to your question, it's the behavior of this T-dualized solution. And I'm currently talking about the chunk between 0 and horizon, which where I have to apply time-like T-duality. So I equals 0 is the image of the singularity, which is mapped to a singularity. The Ritchie curvature in the string frame is divergent. Image of the horizon is indeed a curvature singularity. Ritchie curvature also diverges there. What does the dilaton do? Close to the image of the singularity, close to minus infinity. When approaching the image of the horizon, goes to plus. Now we can talk about this in swampland language. We are approaching the boundary of the modular space. So what is the distance? We are not quite in the swampland setup because we have done a time-like T-duality. So the scalar manifold that I have gotten out has indefinite signature. But I can compute a meaningful distance by pulling back to the solution I have and compute the length of the explicit curve on this indefinite signature scalar space, which corresponds to my solution. And then the distance in modular space is non-null and finite and infinite. So it's an infinite distance, but the distance in space is finite. And that's why I think one should really, in this case, think about what happens if I get scalar. The light phase is a bit different. Light phase is the image of the singular finite affine parameter, but the image of the horizon can be an infinite affine parameter. But the spatial direction, at least, is finite. So it's, I think, legitimate to physically worry what happens in these situations. Now, let's try to interpret this. So for the dilaton determines for the string coupling, at r equals 0, we go to 0 coupling, close to the image of the horizon to infinite coupling. This is, in fact, the same behavior that's also shown by the 10-dimensional dilaton and string coupling, because I can embed it in this universal way, where this corresponds to Calabi-Yau compactification, where all geometric moduli are frozen. So 10 and 40 coupling are forced. And then string coupling gives me the ratio between Planck scale and string scale. So if I have string coupling to 0 at fixed Planck mass, it says tension goes to 0, which by inspection of the mass formula says what we should expect get is tensionless strings, meaning all the excitations of a string become masses. We get an infinite power of mass state with a tension string, which is one of the things that are also discussed in the swampland picture, where it roughly says if you go to the boundary of the model space, you get tower of massive states becoming light and ultimately massless. And should be either come from tensionless strings, so this is the situation of zero string coupling, or if it's related to geometric modulus, it might be decompacted. Now, the T-dual of the horizon is a bit more delicate because dilaton goes to infinity, string coupling goes to infinity. I've expressed my skepticism about S-duality, but let's suppose that I'm in a situation where I could use S-duality. Then I could say, okay, I got a dual description where strong coupling is mapped to weak coupling of some dual population, and then I would conclude it's some kind of dual string which becomes tensionless in this limit. And that, if we buy into this Swampland argument, is the only thing which makes sense, because there's no geometric modulus which could lead me into decomplexification. Okay, what can one now do in order to investigate this further? Because I think one should really get an idea of what is happening at these points. One thing which is said to be associated with tensionless rings is the higher spin theories, which are able to describe a space where you have infinitely many light or massive particles. Maybe less complicated would to look into the various generalized geometries which have been described and which go under various combinations of the term generalized, double, and exceptional without the geometry of field theory. But broadly speaking, I understand that the idea is we want to have a democracy among the masses, closed string modes, and not single out the metric that we are usually doing. And I think that is something that I'm started to look into this defender for that. Again, it's the most minimal version, which is not generalized geometry where you work with intention tangent functions. Okay, but this is work in progress. I can't say that it's complete. Reword of the 10 or 11D perspective. So my student Pope has lifted this up to 10 dimensions. You find the same brain system as for the STU, for example, 11D triple intersecting M5 brains with planar weight on top, and then the type 2A and type 2B version. Difference compared to an STU black hole are as follows. We impose planar rather than spherical symmetry, which means that the harmonic functions that we put into the brain system are delocalized in two more directions, also in X and Y. Normally, for the STU black hole, would point like localized in 3 space dimensions. We just take this configuration smeared out in two more directions in space with scalar planar rather than spherical symmetry. The planar symmetry also the effect that if we have a horizon finite distance, the solution must be non-extremal. If it takes the extremal limit, we just have a naked singularity because the horizon is pushed off to infinity. The planar symmetry also prevents us from having asymptotic flatness compared to the spherical version of non-extremal rise and Nordstern. We lose the exterior region in the conformal diagram, which contains asymptotic flatness. But as I mentioned before, it can be interpreted as a cosmological solution. But for me, having a non-extremal horizon is what I want anyway. So I'm quite happy with this. T-dual solutions should lift up type 2 stars, so then we should get exotic brethren of these brains, but we didn't have time yet to work this out. Good, that's why I am. A few things I could have talked or prepared to talk about, but about, obviously for lack of time. People are working on just construction classification of solutions. Giving you here a few titles just to give you a flavor. Don't ask me too much detail about detailed contents, because it's still also on my to read the time file. Originally, I also wanted to talk about the concept of so-called allowable complex metrics, because that's an idea. So roughly what's the idea here? The idea is to find a criterion which says which complex path you can take in a Euclidean path interval for quantum gravity. Witten had a look at this concept of allowable metric and what it does in certain examples in the paper some time back. It's based on earlier work by Lucas and Strontian. The concept of allowable metric comes from Konsevich and Siegel in a slightly different context. It's about axiomatics of QFT on curved spacetimes, and they proposed coupling to a certain class of complex metrics as a substitute axiom for QFT on curved spacetimes. And Witten took this up and tested out whether if you apply this allowability criterion in the context of Euclidean path interval for quantum gravity, whether it gives you sensible results. And there was some follow-up work on this, but I don't have.
So far, the methods are real. No. The metrics you have talked about are real.
Yes, I've restricted myself to real. So of course I can go super bracket through the complex domain, just continue. But everything that I have talked about was real. Right. Okay, so as I said, I would have liked to talk also about complex metrics, but we neither have the time to talk about, nor did I have the time to read enough. But if you're interested, here is you should be able to retrieve the references. Let me make an attempt at conclusions given out. Like, so we see that if we decide to take time like t seriously, we are led into a world of exotic theories which seem to violate a lot of our preconceptions of what is reasonable. But my impression is we only have the choice to accept this whole package wholesale or accept it and make sense of it. It's an obvious option and legit to discard all these things as unphysical, but doing this ad hoc is something I don't like. It is also against the logics that I had that I explained how we normally proceed in string series by letting us being guided by the symmetries and structures of the series. You would like to have a clear and understandable demarcation criterion, but, and this is which relates to this complex metric story, if you then look at concretely proposed demarcation criteria, my impression is they tend to cut a little bit too much because they reproduce the most conservative physics it could think, but they cut out either things that would be interesting new physics, or even, as far as I can see, cut out some cases that we would like to have included in string series, like some complex saddle points corresponding to rotating black holes, which are used in localization arguments for matching microscopic with macroscopic entropy attractors, in a sense. So one would need to check whether this cuts out, because there's one point that I can say about the little paper. He clearly says the so-called generalized Euclidean metrics in the sense of Gibbons Hawking, and this includes Kerr Newman, are not allowable. Also, cosmology, no boundary is allowable. Elenching tunneling from a contracting to an expanding universe is not allowed. So it's a good criterion in the sense it's quite sharp, but I feel if you believe some of the things that are taken for granted in the string community, it's a bit too much, which it cuts off. That's my initial impression. Now, another point here, which I've already mentioned, our intuition. I think our intuitions of what is physical may be just tied to us thinking about the metric as somehow privileged, but duality in string theory point towards democracy among master string modes. So that's why I have become interested in concepts around all these general geometries. And drawing it a bit more wider, the deductions that we get out of all these theories may give us point about the hidden symmetries which underlie string theory. And of course, this concept of hidden symmetry applies more generally to gravity. So to add something to it, sometimes I like to call it to myself as should we have a stringy Erlangen program. So Felix Klein's Erlangen program was the idea to characterize classified approach geometry through algebra. We first stipulate the group symmetry structure and then construct geometrical structures that realize this. So this logic would be we don't start with the Minkowski space, we start with the Poincare group. The Minkowski space is then the natural symmetric space associated with it, and Riemannian space-time comes about by considering geometries which are locally modeled on Minkowski. We should also, of course, then blend this with hidden symmetry, which somehow seem to be competing with manifest space-time symmetry. There's a famous chain of U-duality, which you can, depending how brave you are, follow down even to 0 dimensions. These U-duality groups come in 2 types: as a continuous group action on the full theory, which is the symmetry of the master spectrum but deforms the method spectrum, and then a crystallographic subgroup, which is even a symmetry if you include the method spectrum or the part we have control over, the BBS. If I have only gone down to 3 dimensions, if you go to 2 dimensions, these algebras become infinite dimensional. They contain the so-called Gerow group, which is related to integrability in Einstein gravity. If you go all the way down, then you get the structure referred to as 11, which, as has been observed, automatically includes all the exotic type 2 and M series. So from this point of view, it would be artificial to exclude them. But even if you don't want to do 11, these exotic series also are quite naturally from the point of view of, say, exception field theory. And it might provide a more handy tool to think a bit more about this. Linking up to what Gabriel is likely to talk about, integrability in gravity. Once we go, if we are in a situation in gravity, 4-dimensional gravity, we will consider solutions to commuting isometry, we can effectively reduce to 2 dimensions, and then we find an infinite dimensional symmetry and have an integrable system being equivalent to solving the equation of motion, which one can equate symmetric factorization problem. This is, if you like, a mini example for an emerging spacetime, because your spacetime has somehow disappeared into integrable system or into matrix factorization problem, and you have to extract it out. Now, one feature which it shows, and which we have also seen in 3D, is the further we dimensional reduce, the smaller the pieces of space-time are that we get out of it. So we have seen in 4 dimensions, I can go across the horizon. If I go to 3 dimensions, it's split up into 2 regions which are somehow need to connect. A different work example is with people like Gabriel and Christina had a Schwarzschild and observed that if you want to describe the Schwarzschild space-time in this formalism, you don't even have only 2 pieces, but even more pieces, because the interior of Schwarzschild appears when it comes out of this matrix factorization as small as many smaller pieces which you seem have to put together. So that's I think it's a communality of observations and pointers to some things which we might want to develop in the future. Okay, adding some wild speculations, not very original. I think many people think and feel along these lines. So let's go over the mythology. So I mentioned space-time and hidden symmetry somehow seem to be competing. So we might dream that we could find a suitable democratic standpoint. Everything is organized as an infinite dimensional algebra. And then we might hope that physics is some kind of gauge theory based on such an algebra. The space-time is just the geometric realization of this geometric structure, and the particle strings and planes are just the excitations that we observe in some limits. Of course, it's sufficiently vague, not only to fit on string theory, but I think it's nice to have some big picture idea in these projections defined. More concretely, what would help, what would maybe an artificial intelligence say be able to help me? So typical, I think, is solving deformation problems. So one is localization of brane solutions. Applied example is de-dualizing my solution. I found something which looks like this. I would be interested in a solution where I lose the isometry, but still solves the equation of motion by allowing the dependence on t. That would be helpful for me to relate various spacetimes that I can generate by T-duality, which look similar, like parts as a family, but which do not connect immediately to each other. And I call this localization because it's a similar story as when you are T-dualizing DP branes. You do not just apply the Boscher rule, but you also need to augment the harmonic function to depend on one extra variable to localize. Now, this is along this line that I think about this problem. Another thing is heating up extremal solutions. So this line element here can be read as a particular parametrization of the planar Reisner-Nordström solution that I showed you. This way of writing it, it depends on 2 functions, h and w. as I mentioned, this solution is non-extreme. Its extreme limit would just not have this function here. So a typical heating up problem would be, if I know this solution, is there a systematic way for me to see that this contains a larger class of solutions which depend on one additional function? So just for clarification, in the solution I showed you, this function h and w were put together into this one single function f of r, which, as you may remember, had two parameters, a mass-like parameter m and a charge-like parameter e. In this way of writing, it's a charge-like parameter e resides here, and the mass-like parameter, if different from the BPS bound, is encoded by an extra non-extremality. So that's why it would be good to have some idea of making this deformation. And it is somehow related to preservation of integrability, in particular if you have a symmetric scalar Kleiner spaces, because finding these solutions is equivalent to finding geodesics, or more generally, totally geodesic submanifolds on the scalar target of the dimensionally reduced theory. Deformation from going non-extremal to, going from extremal to non-extremal corresponds to a deformation rate from null geodesics or null geodesics. So again, the point which might link up to what David is talking about the deformations preserving integrability. So that's, I think, a topic which brings. Then to end on a light note, what is it like not to be a bat, but to live in an exotic world? So I don't know, but science fiction authors have been about it. Humans as gods, the classic of Soviet science fiction. I must have read it in the 80s. And it's an opulent space opera. In the third volume, it employs the big rotation to make time complex to drive the plot along. Thanks to my student Maxime, I also became aware of the work by Greg Egan. He also has a webpage where he explains geometry underlying his novels, which even for hard science fiction is quite something. The Diakonos, I've heard this because it's currently free on Amazon Prime. Book is about living in signature 2,2, and I can tell you it is weird. And I look forward to listening to his authorial trilogy, which will explain how it would be to live in a Euclidean. Thank you, Bob.
Questions?
There are examples of the solutions changing the number of the state. Are there examples of these kind of solutions changing the number of plus minus signature in ADS CFT context on the supergravity side?
Yes, so you mean this exotic holographic duality?
Well, perhaps they are
no, or do you mean this PP wave, which I showed you in this where you outside have Lorentz spacetimes, the naked singularity, and inside Euclidean?
Yes, what do you mention that you have this change?
Yeah, I mean, I showed you that in fact every non-extreme event horizon is in a sense an example. But the other example was a PP wave. It shows a harmonic function which has a simple zero. That was the negative. This was the left of the D0 brane. So negative D0 brane in Lorentz signature is a positive D0 brane in Euclidean signature, but it comes from lifting it to a PP wave in 11D supergravity. Yes, that was the example. That's from this digraph buffer wave.
But I mean, the interesting question would be to see what is the meaning of that foundation. I mean, one can use it against it. Right? What is the meaning of that change of signature?
Yeah, the signature change itself, I haven't seen anybody. I mean, people do kind of holography in these exotic backgrounds, but describing signature change from this point of view, I haven't seen any. So it's an idea.
Other questions?